After we covered quite a lot of models in data mining, such as linear regression, logistic regression, linear discriminant analysis, decision trees, association rules, and clustering, etc. I believe this is a good time to make a comparison between what you have used in the past to create, for instance, a linear regression model, and how you used to evaluate that model, in contrast with what we are doing here in data mining, and the reason behind not looking at the actual model after we generate it. So as you recall, we never went back to look at the p-value of the generated linear regression model or the logistic regression model, to also look at the assumptions, statistical assumptions of if those models are correct or not, or are they the best fitting models to our problem. So it's good to go and recall what you used to do in the past in statistical linear regression models, and just to compare it with data mining. And that will be the introduction to the different type of modeling and evaluations used in data mining. And this way you will know and you will justify why until today we didn't look at evaluating the output of our models in the last 10 examples we have been working on. So first of all, let's recall what you used to do in your statistical courses. So when you try to create a regression analysis, all what you are trying to do is that you are trying to find or to understand the relationship between several variables and maybe the response value. So we usually in the past we start looking at the variables and create a scatter plot just to see if there is any relationship between those variables, and you try to explore if there is a potential relationship between pairs of variables as a starting point. Then you used to move to an upper level of analysis, which is correlation. You try to see if there is any relationship between two variables, pairs of variables. And even with pairs of variables, you look at the value of R. For example, here the value is 0.921. It's very high, and it is a positive relationship. One of the variables going up and the other one is going up as well. So if this is your Y, this is your response, and this is your predictor, so you can tell there is a strong correlation between the response and between response and the predictor, and it's a positive relationship. Whereas the second pair, you can tell yes, it is high relationship, 0.921. However, this is a negative relationship. Where you go down, you can see this is a very, very small value of correlation, R equal 0.038 minus. So you will say over here we have no correlation between the response and the predictor. However, as you can see, the correlation failed to give us a relationship between two variables here, not because there is no correlation. There is a correlation, and the type of this correlation is a curve type of correlation. But correlation is not sophisticated enough to identify this type of correlation, but it's our job to see how the scatter plot is look like, and accordingly we might decide to look at more sophisticated relationship between pairs by creating a linear regression or a regression modeling, or what is called statistical modeling. That's what you used to do in the past. You're trying to find relationship between the output variable that could be called response and the input variable that called also factors or explanatory effect or predictors or x's, where the output we might call them response based on the application you're using. All of them are the same, or dependent variable or the outcome or y. So you start building your regression model accordingly. Okay, and now you might have many different type of regression models, simple, multiple regression model. So it depends on the case that you are studying. Now, as a regression model, all it does, it finds relationship between those input variables and the y. Some of them will contribute to the model and some might not. This type of analysis is called explanatory modeling, and that's what you have been doing in your past. In your statistical courses, that's the type of analysis that you have been working on. However, there is another type of analysis that you can use regression model in, which is the predictive modeling, and that's what we have been doing in data mining course. We were looking at finding the y value, which is, let's say, the second heart attack case scenario. We were trying to find if a person's gonna have second heart attack based on the variables we have in the past. And some of those variables could be the weight, could be the cholesterol level, it could be the gender with relation to those two other variables, it could be maybe having some type of attending workshops to train how to manage weight can contribute to lowering your chances of having second heart attack, etc. This is what we were working on during the semester. So you might start with a simple linear regression, which is just one the y with a relationship with one variable. Here is you are going to look at a fitting model that is the best fitting model for your data, and how you come up with your y, your equation, which in case when you have just one variable, we call it the mean of removal, mean of y, and you explain the relationship between the y and your intercept of your, so this is the intercept of your fitting model, which is 4.099 plus the slope coefficient of your fitting model. And you interpret the relationship between those two variables by saying the following: every 1 unit increase of the variable OD will yield to an increase in the y equivalent to 0.5284. Okay, so that's what we used to do historically. Now, if you recall that you come up with this fitting model, but that fitting model is just one estimate of the true linear model that can fit the population. So the way we used to run the statistics, we would say, okay, well, you have your population that might contain a lot of observations, but you're not capable of creating a model for all the population. For example, if you want to look at the second heart attack of the whole people in USA, that's really difficult. However, you have maybe the data of Bowling Green, because we only have 2 hospitals, so you were able to obtain the data of the patients in Bowling Green, and those are sample of the population, and you created a linear model. The relationship Y was maybe having second heart attack, and the OD, instead of OD, imagine this is the cholesterol level. So a simple linear regression model for only one variable with your response Y. Now, the idea always that when you created that fitting model for Bowling Green, you are considering that this model should work for every other city in Kentucky or in USA. So if every time you bring in new data from different cities, new samples, your model should work as well. And how we did test this type of hypothesis, we used to have some type of measurement to evaluate our models. Okay, and just to remind you a little bit how you evaluate and how you create the model first. So when you create your fitting model, the idea is you create a theoretical model where the mean of Y for your axis equal to the beta 0 plus b1 x, where b0 is your intercept and b1 is your slope. And the idea is you're trying to fit this line in a way that it minimizes the error. Now you have to interpret this value from your standpoint. So all you have to try is you are trying to find the best fit where the total variation in your response can be broken into two components: the variation explained by our model and the unexplained variation by the noise. And the sum of squared t for all of them, it's equal to those both summed up. So this will be the one that the squared error explained by the model, and those who were not explained by the model, which is considered as the error that we have in our model. Now, the smaller you get your error, the better your model is for that specific situation. So the error sum of square, or SSE, is a measure of random error or the unexplained variation in the error. And as I said, usually you sum them up to get the total sum of square. And the bigger is, here is an example here, if you have a model where your total sum of square, as we said, equal to sum of square of error plus the sum of square of the model. If the model is capable of explaining a lot of the variation of the model and where the error is very small, so that's a very good model. In this case scenario, you can see that the value of your model here, the mean square the square mean, the sum of square equals the sum of square analyzed by the model, which is this big value over here is 319, where the sum square of the errors here is 1.26, which is very small. So the ratio is going to be very big, which is good. That means the p-value is going to be very small, and accordingly we say that this model is capable of explaining the variations in this model. And also, if you remember, you look at what is called the R square, and if you can think about it for simple linear regression, that's easy. R square is the square of the correlation, and as we say, the correlation usually is nothing but a value between -1 and 1. We are squaring here, so it's going to be a value between 0 and 1. What you say here, 84% of the variation of your linear regression model can be explained by this equation y equal 4.099, the one we saw, plus 0.52 OD. So the model is capable of explaining it. We talk more about the adjust if you have multiple regression model. So as you can see, you use this type of analysis, and the R square is nothing but the division of the sum square explained by the model over the sum square of the total, which equal to the model plus the sum square of the error. So that's how statistically you could prove that this is the best fit of my model, and accordingly now you move to the other assumptions that you have to prove that they are also correct to finally decide that this is the best model. What else? Now you build all your statistical model based on some assumptions. So we say this model is a good model for our data. However, we have to test and evaluate if the assumptions of a good fitting model is really met. If you remember, beside the assumption of equal variation, they are independent. There is no some type of autocorrelation between the response and the predictor value variable. So that's another thing you have to look into and to make sure is not happening. Otherwise, you are considering this is a problem for you. Also, you look at the residuals, the sum squared errors. Are they normally distributed around, like there is they have a constant of variance, the approximately is normally distributed, independent one from the other. So you plot the residuals against the predicted, if you remember. If you don't see any pattern, you say that's okay, this is so far my considered fitted regression model is okay, because there I don't see any type of patterns when I plot the residuals against the predicted. What else? If you see some type of curve relationship, as you can see here, between the residuals and the predicted, then you reject this model and you will have to come up with a different model. You can see there is a quadratic type of relationship, so maybe your model is a quadratic type, so you try to use a quadratic equation for your predicted value in your equation. Another problem, if you recall, in your statistic you look to see if there is a pattern of funnel type between residuals and the predicted value. So if it's there, again you cannot accept that model and you have to look at different type of models. Outliers, if there are outliers when you plot those residuals with the predicted, again that's a big problem. Also, if the approximately is it normally distributed, those residuals, so you plot them and you look, there is nothing not normal or going maybe in a very like outliers over here outside those density, that the red line, so you will come up and say, yeah, it's not normally distributed, so you might not consider that model. So all those type of evaluations that and testing the assumptions of a good fitted model, that's the things that you have been relying on in your statistical evaluation models. Now, in the predicted models, we are not going to do that. In the data mining, that's not the scenario that we're gonna use. However, we're gonna rely on something totally different, and the next video we're gonna start to investigate how you can evaluate a model and how you can decide which model, like we had in one case scenario, we used 3 different models. We used the linear regression and logistic regression and the linear discriminant analysis on the second heart attack data. And accordingly, we said that's more better model than the other, only because we were able to see the confidence level in the output. However, there is a way to detect which model among those three is the best. Okay, and that will start in our second video.